Hello, world, universe, etc. So today's lesson we're going to look at solution stoichiometry, in which our compounds are in water. So we're going to be talking about things like concentration and such. Okay, so your lesson objective is to be able to solve problems involving concentration, and we're talking about molarity there. The number of moles and the volume of solution. So by the end of this lesson, you will be able to do this. You can do it. Okay, so let's get into it. First, solutions are what we call homogeneous mixtures of a substance composed of at least one solute and one solvent, and these are vocabulary words that you should know. Homogeneous just means that the solute is evenly distributed through the solvent. For most of our cases, our solvent is going to be water. And then our solute will usually be various salts, okay? Not necessarily every single case, but most of the cases we will be looking at. Other solvents include alcohol, very common solvent, and there's other stuff as well. So a homogeneous mixture is a uniform mixture of only one phase. A solute is a substance that is dissolved in a solvent. Okay, so we could be talking about salt, in this case sodium chloride, but remember that salts can be all kinds of stuff. The solvent is the medium in which a solute is dissolved, and often the liquid component of a solution. As I said, usually we're talking about water. Concentration is a ratio that compares the quantity of solute to the quantity of solution. Okay, the total quantity of solution. Okay, so next, molar concentration is the quantity of solute in moles dissolved into 1 cubic decimeter of solution, or 1 liter. And let's be very clear here. Let me throw this out there. 1 liter is equal to 1 decimeter cubed. Okay, so they can be used interchangeably, and they often are. So just so you know. Okay, so molar concentration can also be indicated by the use of square brackets. So for example, the molar concentration of sodium hydroxide in water could be represented by NaOH aqueous in brackets. And what that just tells us is that we're dealing with a concentration. And that's it. So first example, time to do some math. Saline solution contains 0.90 grams of sodium chloride dissolved in 100 milliliters of solution. What is the molar concentration of the solution? Express your final answer in moles per decimeter cubed. Okay, there you go. I will wait. Haha, little joke there. You don't know what to do yet, so that would be cruel, and I'm not that mean. So let's start by giving you a formula. Formulas are always good. So the formula that we need here is defined right here. Concentration is equal to the number of moles divided by volume, okay? And this also gives us, you will notice, our unit for concentration, which we've already discussed, is going to be moles per cubic decimeter or per liter. Okay, so I should actually add that here in liters or decimeters cubed. Okay, so there we go. The setup. As always, we need to define our variables. So here we've been given a volume, and that volume is 100 milliliters, which we should convert to either liters or decimeters cubed. And again, just remember that this would be equal to the same number of decimeters cubed because they're straight across the board equal to each other. In this case, though, our problem is given in, actually it's given in decimeters cubed. Doesn't really matter. We'll cover that momentarily. Okay, we know our mass is 0.90 grams, and that's all well and good, but for concentrations, we need moles, okay? So to give our concentration in terms of moles per decimeter cubed, we have to convert mass to moles. So we're going to do that next, and you guys should be very familiar with that. The first thing we're going to need is the molar mass, and we've not calculated that, okay? So we need to calculate the molar mass of sodium chloride, and you guys have already done this yourselves on multiple occasions. So we take the molar mass of sodium, which is 22.9 grams per mole, and we take the molar mass of chlorine, which is 35.5 grams per mole. Remember, we just get those straight off the periodic table, very easy. And we add those two masses together, molar masses together, and we get 58.44 grams per mole. Done. Nice. Okay, so now we have a mass and we have the molar mass, so we can calculate the number of moles. And what we will find after plugging in these values into our very handy equation is that we have 0.154 grams per mole. Note that grams here will cancel out, and this is one of the reasons why I always leave my units in when I do calculations, because this inverse mole in the denominator will become a regular mole after we finish doing our algebra with the units. Okay, so there's the whole slide. If you want to pause for any reason, we're going to move on. Okay, so now we've defined the variables, and we know from this equation that we can calculate concentration from the number of moles divided by volume, and now we have both of those variables. Okay, so now it's just a simple matter of plugging them in and doing some very easy algebra. You may wish to use your calculator, but you don't really need to for this one because the denominator is very easy to work with. What we find is that our answer is going to be 0.15 moles per decimeter cubed. And the reason why that is decimeter cubed is because of this conversion factor where 1 liter is equal to 1 decimeter cubed. Okay, so I was working here with liters, but it doesn't really matter. As I said, we can just scratch off this L anytime and plug in decimeter cubed. They're absolutely equivalent, at least for our purposes here. Okay, they are a volume. Okay, there's the whole slide, and there's our answer, 0.15 moles per decimeter cubed. Whoa, gesundheit. Two significant figures. There we go. Okay, another problem. At 20 degrees Celsius, a saturated solution of calcium sulfate has a concentration of 0.0153 moles per liter, and a student takes 65 milliliters of that solution and evaporates it. So when you do that with a solution, what you will usually find is that when the water is gone, you still have your solute. It will crystallize, okay? And because of that crystallization, you'll end up with some nice crystals. In this case, your crystals would be calcium sulfate. I'm not actually sure what those look like. I'm curious. We might have to try it. Excuse me. So the first step here, guys, will nearly always be to find the molar mass. You don't have to do it first. You could do another thing first, but in this case, we know we need it right off the bat, and that is because of our formula, which you'll see here. This formula dictates that we're going to need our molar mass, so it's a couple steps down the road. But in any case, the key word here that would indicate that you're going to need the molar mass is pretty straightforward. It's just mass. Okay, so if we have to find a mass and we're given moles per liter, we know that we're going to need to convert moles to mass at some point. Okay, and if that is the case, then we need our molar mass. And there it is. Okay, so for our formula for calcium sulfate, we have 1 calcium atom in the formula, or ion if you prefer, and we have 1 sulfur, and we have 4 oxygen. Okay, so that gives us multipliers. Again, we get our molar masses for each element from the periodic table. 40.08 grams per mole is for calcium. 32.07 is for sulfur, and for oxygen we have a nice even 16.00 grams per mole. Okay, so we add these up and multiply our oxygen by 4, and we get 136.15 grams per mole for our molar mass. Again, doesn't have to be the first step, but it's generally a pretty good move. Okay, next we find the number of moles in 65 milliliters of solution. We could do this first, doesn't really matter. We're going to have to do both steps one way or the other. Okay, so here what we need to do is convert our volume to liters, in this case, rather than milliliters. And that's an important step. Don't forget to do that. You could also convert it directly to decimeters cubed. Again, that's fine. Doesn't matter too much. So we are given the concentration, and it is 0.0153 moles per liter. Okay, so we know that concentration is equal to the number of moles divided by volume. So with some very basic algebra, where we multiply both sides of this by volume, we get N is equal to concentration times volume. And from here, we can just plug in our numbers, and we will find the number of moles of calcium sulfate in this solution. Okay, so useful information. And you'll note that we also know our molar mass. So it's all starting to come together, isn't it, chemists? So here we've defined our variables. It's never a bad idea to do that. So we don't know the mass. That's the final question, and I've identified that variable with some question marks. Once you've identified all the variables that you have, it's very easy to pick the equation that you need in order to solve for the unknown variable. So in this case, we don't know mass. So we solve this equation for mass, and we find that mass is equal to the number of moles times the molar mass. Okay, so then we just plug in our numbers, and now we have some very basic algebra. We've got some pretty big numbers here. We have more significant figures than we need, but that's okay for intermediate calculations, as long as your final calculation includes the appropriate number of significant figures, which in this case is 2. Okay, all right, so next, a couple of vocabulary words. Standard solution is a solution of known concentration. So if you were a chemist in a laboratory, you would either make your standard solution from solid, and you've now seen some of the theory that you would need to do that, or you would buy your standard solution from a supply warehouse. A good chemist should be able to make their own if they need to at any time. Concentrated solution is a solution that contains a large amount of solute relative to the amount that could dissolve. So basically, a concentrated solution is holding the maximum amount of the compound at a certain temperature. So if you change the temperature of the solution, the amount that it can hold, the amount of the solute that it can hold will actually change. Future experiment question, perhaps. Research question. Okay, let's look at another problem. For a class experiment, your teacher must make 2 decimeters cubed of 0.1 mole per decimeter cubed sulfuric acid. This acid is usually sold as an 18 mole per decimeter cube concentrated solution. How much of the concentrated solution should be used to make a new solution with the correct concentration? Okay, go ahead and get started. I will wait for the solution. Just a joke. You've not seen the theory that you need to do that. So let's take a look. In order to answer this question, we're going to need a new formula, but it's actually our old formula. So we start with concentration is equal to the number of moles divided by volume. Now, what we're going to do is rearrange our equation and assume that concentration times volume divided by the number of moles is a constant. And if you're wondering how I got that, it's just by taking our previous equation, C is equal to N divided by V, and dividing both sides by V divided by N. And then we get this convenient formula here. Okay, so we assume that C, concentration times volume divided by the number of moles, is constant, and in fact, it actually is. So what that means is that if we change one of those variables, then that is going to have a predictable effect on the other variables. And what that gives us then is proportionality, where we have this relationship between the initial conditions and the final conditions, or in this case, the desired conditions. Because usually in chemistry, we have a desired outcome. We want our solution to have a certain concentration, and we will want a certain volume of that solution. Okay, so here then is our starting formula. Oh, that's not good. How did that happen? Okay. Yuck. Okay. So initial conditions are equal again to desired conditions, or final conditions if you prefer. Now, in the case of a dilution, all we're going to be doing is adding water to a solution. So what that means is the number of moles of solute, and remember that is what we're dealing with here, is going to stay constant. Okay, and if that is the case, then we can simplify our equation. Okay, so because the number of moles of solute is going to be constant, that means that they're equivalent, and they will just cancel out of our equation. Okay, so what we are then left with is our initial concentration times our initial volume, and that will be equal to our desired concentration multiplied by our desired volume. Okay, so this is a very simple equation, and this is all we need to solve this problem. And it turns what could have been a very difficult problem into actually quite a nice, easy problem. Okay, although you do need to know that equation. Okay, so we begin then by defining our variables as usual. So if you misidentify your variables, that is going to mess up your calculation. So be careful here. So our initial concentration will generally be higher than our final concentration for a dilution, right? We're diluting the substance so it's less concentrated, okay? So that means that our initial concentration generally is going to be higher than our final or desired concentration. So that's what we start with. In a dilution, we generally aren't going to know our initial volume, although we could easily set up a problem in which we did. but it's not usually the case. So then our desired concentration, obviously we know we want a 0.10 mole per decimeter cube concentration of sulfuric acid. And our desired volume is 2 decimeters cubed or 2 liters. Okay, so now, and this is awesome, all we have to do is solve for initial volume. So this is the initial volume of solution. So this is the volume of the 18 mole per decimeter cubed solution that we're calculating for now. Okay, and all we have to do is plug in our values and either plug this into our calculator or do it in our heads or on the back of a napkin. Doesn't really matter. In any case, what we will find after we complete our calculation is that we require 0.011 decimeters cubed. Okay, and that will give us 2 liters of our desired concentration. Okay, next, one more problem. And here we probably have enough information for you guys to attack these based on some of the previous theory that we've covered in class. But regardless, I'm going to show you how to do it because I'm a nice guy. Okay, so first, calculate the concentration of chloride ions in each solution. So in order to do that, the first thing we need to do is find the number of ions in there. And the way that we do that is by finding the number of moles. And of course, we're given a mass in A. We have 19.8 grams of potassium iodide. And we're given a volume. So we can identify those immediately. And it's always a good idea to do that. If you are given a mass, you're probably going to have to convert it to moles, and the way that we do that, of course, is by first calculating the molar mass, and I've shown that calculation here and explained how we get it. These numbers come straight off the periodic table. I don't think we need to cover it in more detail. What we find is our molar mass of potassium chloride is 74.6 grams per mole. From that information, we plug it into our incredibly useful formula for the number of moles. And what we will find is that we have 0.625 moles of sodium chloride after we plug our numbers in. And again, just one note, grams cancel out, and the number of moles is the remaining unit. Okay, we have a 1-to-1 mole ratio here. So if we have 0.25 moles of sodium chloride, that means we have 0.25 moles of sodium and we have 0.25 moles of chlorine. Okay, so remember, we treat this like one block, and the sodium and chlorine combine in a 1-to-1 ratio, which means if we have 0.265 moles of the compound, then we have 0.265 moles of chlorine. So we then take that value and plug it in to our formula along with our volume, and we get 2.65 moles per decimeter cubed. And here is the entire slide. Okay, so we've solved A. B is extremely similar. The main difference between A and B is, well, first we have a different molar mass, but also our molar ratio is different. Calcium chloride has a formula of 1 calcium for every 2 chlorine ions. Okay, so that changes our molar mass calculation, and that we now have to multiply the molar mass of chlorine by 2. And it also changes how we calculate the final number of moles, because we have 0.23 moles of calcium chloride, but for every unit of calcium chloride, we have 2 units of chlorine. So that means we need to multiply the number of moles of calcium chloride by 2 to get the number of moles of chlorine, which will be 0.477 moles. Okay, so we take that value and again we plug it into our formula along with the appropriate volume, which in this case is 0.150 decimeters cubed. I've not shown the conversion here, but hopefully you are following along. And our answer then will be 3.18 moles per decimeter cubed. And there's the entire slide. Ta-da! Okay, so for our last part, whoa, wait a second. Oh, I have 2 copies of this slide. Oops. Okay, for our last part then, we need to find the concentration of a mixture of the 2 solutions from parts A and B. This could be more complicated than I've made it here. There are a couple of different approaches you could take. And if you take a different approach than I take, generally, I don't penalize students for that. But this is probably the fastest and easiest. So for our concentration, we take the total number of chlorine ions in terms of moles, and we divide that by the total volume in terms of decimeters cubed. So we just take our number of moles from our previous calculations, we add them together, divide it by the total volume of the solution, and we will get the concentration of chlorine ions. So basically we pour one solution into the other one, and then the question is, what is the concentration of chlorine ions? Well, there it is, 2.97 moles per decimeter cubed. All right. Last definition, precipitate is an insoluble solid that is formed by a chemical reaction between 2 soluble compounds. So you will take 2 liquids and put them together, and one of your products will be a solid, okay? And these reactions are fairly common. There's a pretty cool one you can do with lead iodide, but lead is pretty toxic, so I try not to play with it. There's some possibility I gave myself lead poisoning a number of years ago. Okay, so challenge question. You may or may not be up for it. Doesn't matter if you are or not. Here it is. I'm just going to leave it here. I'm not going to read it or go through the solution. We'll just pop it here. Before you do the challenge question, though, you should do the homework, which is given here, and I'm going to confirm that this is actually what you need to do. So I will post your actual homework on Google Classroom if it is different from these, but I think this is probably accurate. Okay, in any case, my name is Ryan Van Loo. I'm a physics and chemistry teacher. Do not click like nor subscribe, and have a great day.